What's up?
What's up? What's up?
That made my day. All right, I've had enough. I'll see you guys Wednesday.
See ya.
See ya. How'd everybody's weekend go?
That was good.
Good. eBay got a haircut.
Yeah.
Dang, boy. What's up, Gavin?
Not much. Still tired.
Tired? You want to go back to bed?
Thinking about it.
Yeah. I'll try not to keep you all day.
Okay.
All right. Anybody have any trouble with the homework assignment that was originally it was due last week and then we pushed it up to today? No comment?
I got it all good.
That was chapter 1, right?
Yes, sir. Cody, where are you at? You look like you're on vacation.
What?
You look like you're on vacation. Where are you at?
Backyard of this house I'm rewiring. Got an
Oh, yeah?
amazing landscape set up. Like that'd be a good school place.
Is that what you do? Does your company always do? Well, you do more than just residential, right?
Yeah, I'm primarily on the residential side, but we also have a commercial division. So.
All right. Well, I figured we'd just go through this together. Wednesday morning. Well, let me see. Can't remember if I lumped chapter quizzes together. Yeah. So we won't take a quiz until we're done with chapter 2. So probably next week we'll take a quiz over chapters 1 and 2. And in the meantime, I'm just going to keep going through lab work and ladder diagrams and all that. But let's go through this together. Dead circuits should be what?
Checked with a meter. C.
Both B and C.
Oh, is it both B and C?
Both B and C. Locked out, tagged out before starting any repairs. Checked by metering voltage. I don't know how much higher voltage experience you guys have, but after this class, you guys will be taking Electech 151, which is troubleshooting, and we're gonna be using your meters to check voltage on different components up to 208 volts, which it's nothing you should have a healthy respect for it, but it's nothing you need to be afraid of. But like the question was saying, locked out and tagged out before starting any repairs. So that's like if you were up in a ceiling, working on some lights, you want to make sure that nobody's got any way to kill you while you're working on something. You know what I'm saying? So in this class, I really don't ask for a whole lot of, I just ask for common sense. I'm really not going to be making you lock out every single time you're doing a ladder diagram. As long as you're being safe, nobody's being too weird, which is kind of funny coming from me, but I take safety pretty seriously. So anyway, I don't know what the hell I'm talking about. Let's just do number 2. A GFCI breaker or receptacle monitors what?
The difference between live and neutral.
Right. It's a difference between current in the live and the neutral. Anybody know off the top of their head how many amps trips a GFCI?
Isn't it a 5 milliamps?
5 milliamps is what I always remember. I think somewhere in one of these books, either your residential book or this book, it'll tell you it's like 4 to 6. I always just remember 5 milliamps. That's a pretty small amount of difference in current, right? Does everybody understand the concept of that, though? It's a ground fault. It's not an overcurrent. It's checking the difference between the hot and the neutral. I guess that's important enough that we should stop and take a look at it, since y'all are looking at me like I have potatoes growing off my face. Let's see how I want to do this. It's just the bare necessities. It's just the bare necessities. Forget about your worries and your strife. Yeah, man. All right. Let me put it this way. Whoop. Oh, man, this is bad. Try this again. That's better. AC source. Oh, my goodness. Simple little circuit. Got 120 volts and a light. If I took, let's say this is just on like a 15 amp fuse right here. Okay, so that's your overcurrent protection device. So one little light bulb, how much current do you think that's going to draw? Very small amount, like less than an amp. Doesn't matter what the wattage is, it's not going to pull very much. That fuse is designed to interrupt the circuit when it reaches 15 amps, right? So if we put more and more lights on there, it's going to draw more and more current. This thing's going to blow. But if I touch this, this is me in all of my glory, and I'm touching the ground, touching the earth. So I reach out and touch this. Is that going to blow the fuse? No, because it's not going to draw more than 15 amps of current through my body. A GFCI detects the difference between and current between this point and this point, because theoretically they should be equal, right? But if I'm touching the ground here, and this is the return path, I'm actually taking some current away from this side of the circuit when I touch this, right? So whatever this current is, if this was 1 amp, this now right here might become like, I don't know, 0.2 amps. And you might have 0.8 amps going through me to the ground. And when it becomes really dangerous is when I'm just got out of a swimming pool and my skin is less resistive to that current flow. Hey, let me mute this. Let me mute my class for a second. Hang on. All right, I'm not muted anymore. Quit talking about my mom. Okay, I'm back. What was I saying?
How'd you know we were talking about your mom?
I wasn't. No, you weren't talking. You were talking about my mom?
I think
Show
it was,
your face. You're going to talk about my mom behind my back. You better show your face. Yeah, man. That's my mom.
What class is this? I want to sign up for it.
150. Come on in, bro. Water's fine. Okay, where were we? Oh,
Speaking of water, you just got out of the pool and touched
just
it?
got out of the swimming pool. That made my skin less resistive. All right, so keep in mind, did everybody see that concept now? If I'm drawing current away from the circuit through my body, if it's more than 5 milliamps, it's going to cut off the circuit immediately. Make sense? All right, so let's keep going through the homework, and you'll see how kind of important that is. Oh, here we go. So a difference in current flow between the live and the neutral conductor. GFCI protects against the most common form of electric shock. I already said it.
Ground fault?
Ground fault. Don't make me start calling on people. I really don't like feeling like I'm talking to myself. Confined space is one that has blank entrance or exit by way of location, size, or means.
Restrictive.
Restrictive. According to Ohm's law, assuming body path resistance of 100 ohms, what amount of current would flow if a person came into contact with 120 volts?
1.2 amps.
1.2 amps. After vigorous testing to UL standards, the product, if it passes, is then referred to as being blank by Underwriter's Laboratory. Listed. You guys ever seen the labels on piece of equipment that's UL listed, Underwriter's Laboratory? You might have all seen it without even recognizing it, but let me find a piece of equipment here. It's this little guy right here. Listed, blah, 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 but that Underwriter's Laboratory is basically a way to tell you that that's a legit piece of equipment that's going to stand up to the ratings that it was tested for. All right, exposed live wire makes contact with the metal frame of an ungrounded piece of electrical equipment. As a result,
All of those.
no.
The metal frame will be live.
Yeah, basically nothing happens until somebody comes and touches it. Right? That piece of equipment is ungrounded. It just becomes on the same potential as the hot conductor until something provides it a current path to do something. So that's why we ground equipment. Capacitors should be what before handling them?
Discharged.
Discharged. Anybody gotten walloped by a capacitor before? It hurts. Anybody know what a capacitor is, right?
Yeah.
The little bitty capacitors that you had like in your parts kit for 131, 132, those probably aren't going to do you much damage because they won't hold a charge that's in voltage that's going to really hurt you. But bigger capacitors, I don't know if any of you have seen them. I can grab one if you're interested in seeing one, but those can hold a lot of voltage. And it's basically like a battery, right? Capacitor's job is to charge, and then discharge whenever it's told to. But if you put your hand or your finger or anything in between those 2 points of contact, like if this is the, can you see me? If this is the capacitor lead sticking out the top of it, if I go like that, and there's a charge in there, that current's going to go through my hand until it dissipates enough energy to stop. But where it becomes dangerous is if this is holding 277 volts worth of charge, and I touch one here and I touch one here, where's the current going to flow?
Through the heart.
Right through my heart, right through this guy, right, my big old loving caring heart. That's going to get walloped, and that's when bad things happen. That's when like your heart stops and stuff. So anyway, don't do that. Oh, and then how do you discharge it? I have a capacitor here. How do you discharge it?
A jumper between the terminals.
Take a screwdriver or your tongue, something like that. Just kidding. Don't put your tongue on it. That would hurt. But that's how you discharge it. You're basically just shorting the terminals together. Electrical what is the process of placing a danger tag on the source of electrical power, which indicates the equipment may not be operated until the danger tag is removed.
Tag out.
Tag out. Generally, any body current flow above something
5
considered
million.
dangerous. 5 milliamps. Huh. Sounds familiar, right? That's why GFIs save lives. Keep material equipment at least how many feet away from high voltage overhead power lines?
10 feet.
10 feet. Usually each utility, like Ameren has their own rule of thumb. Like they have horizontal clearances they want you to stay away from, or vertical clearances they want you to stay away from. And they have different clearances for the three-phase primary versus the neutral and all that stuff. But basically, if it's me, I just stay the hell away from all of it. I don't like being anywhere near that stuff because I'm not trained to be, and I don't have the right safety equipment, right? Anyway. What does moisture do to resistance?
Creases.
Decreases it. What does OSHA do?
Get in the way?
Yep. Anything else?
They set safety standards for workplace and conduct inspection tours to ensure compliance.
Yep. And then fine the hell out of you if you're not doing things safely. What does the NEC do?
Outlines minimum safety requirements.
Yep. And the key word there is minimum. It is the law, but it's the minimum law.
Some French toast casserole. You want some?
Is it going to be there for a bit?
A little bit.
I'll come get some.
Okay.
Thank you. In 216? In 216 next door?
Yep, next door.
All right. Thanks. What is the amount of current flowing through the body equal to?
Voltage divided by resistance.
I equals E over R, same as any other Ohm's law scenario. Shock intensity, what?
All of them.
All of those. These are the three. These are the three main factors that determine the severity of somebody getting shocked or electrocuted or hit or bit or whatever you want to call it. The severity of it depends on, it's all current. And I can argue with you about current versus voltage if you want. If you want to go there, we can. But I will destroy you in that argument. I'm just kidding. But if you want to know, ask me later. Anyway, amount of current flow through the body, or current path, and the time you're exposed to that current. Those are the three things. The purpose of bonding non-current carrying metal parts of an electrical system is
I think it's all of those, right?
does all of them. You want it to provide a low resistance path for fault current because that's what's going to trip your fuse or your breaker or whatever's there to protect the system, protect the wire. Limit the touch voltage when metal parts are energized by a ground fault. Facilitate operation of overcurrent protective devices. When a current is still applied to an unconscious victim of electrocution, your first priority is
Turn that off.
kick them in the face. That's what I do. See if they wake up. Just kick them right in the face.
Sounds like a plan.
I'm just seeing if you guys are paying attention.
That to poor Steve.
Turn it off if you can, safely. When installing new machinery, ensure all the metal framework is efficiently and permanently grounded. Why? Why do we ground the motors on our trainers?
Minimize the touching shock and then provide a path for fuse to trip. My previous question, those three answers.
Yep. Yeah, I mean, you're reading the stuff off the homework, but if remember I showed you the guts of a motor, you got all those little windings in there. One of those burns up and ends up touching the outside casing. You would want a fuse to blow, right? You would want that to happen, because if it doesn't and it just sits there energized, as soon as you come up and touch the casing of that motor, you're going to get licked. That's what you want to happen. When operating a disconnect switch, all of them. I always tell people even if it's closed, just look away and flip it on. And if it's open, you guys know what an arc flash is? Or an arc blast?
Oh yeah.
Yeah, it's like a short that's like in the air, basically.
Yeah, it's when the air around the conductor becomes ionized, and it's basically an explosion that you have no warning if it's going to happen. You're pretty well protected if the thing is closed, but you should always be wearing safety glasses. If I'm doing this and then I turn it on, if there's any metal shavings or anything in there that could cause an arc, it could create an arc flash. Anyway, the safe habit to get into is just to look away from it. And then I always inhale and then do that, because if there's an explosion in your face, what do you think your first reaction is to do? Go, you know, and you don't want all those hot gases going into your lungs. So it's just a good practice to get into. It makes you look kind of funny if people don't know what you're doing or why you're doing it, because they think, well, that guy doesn't trust his work very much if he's going, you know, and then turning something on. It makes me look like a dumbass. But those people have probably never seen a video of an arc flash. You know what I'm saying? Pretty scary stuff. Anyway, rarely happens, but it's just a good habit to get into, to stand away, look away, hold your breath. You can do however you want to. You don't have to try to look like a dumbass in class just because I'm telling you to do it. But anyway, what were we doing? Oh, this. What's recognized testing laboratory?
Is it all of them?
They're looking for UL. I mean, National Fire Protection Agency, National Electrical Code, they don't test equipment. They just tell you what the minimum installation requirements are for things. What is a GFCI? Oh, we just did this one, 5 milliamps. What is the intentional connection of a current carrying inductor to earth?
Grounding.
Grounding. What is the joining of all non-current carrying conductive enclosures together?
Bonding.
Bonding. Does everybody understand the difference there? Let's say I got two boxes, two little handy boxes here. And I'm gonna put receptacles in there. And they're joined. So these are metal, and they're joined by a piece of PVC conduit. Is PVC or plastic conductive?
No.
No, it's not. So if this one happens to be connected to earth ground somehow, is this one grounded?
Yes.
Is this one grounded?
Nope.
No. So what do we need to do?
Run a ground wire from that box to the other box.
Right, and that's called bonding. So if this is a PVC conduit, get my colors here. Shit. Shoot. Oops. What? Where can I see my damn colors? Whoa, there we go. Sort of green. Anyway, from this point, there's going to be some way to put a little green screw in here. And if I run that wire through that conduit and make it up in here, then I'm bonding those two pieces together. Now, this one is grounded, right? Through this green wire into earth ground. So that's the difference. Bonding just means you're bringing two pieces of equipment together and making them electrically continuous somehow. Everybody got it? Questions on the homework?
No, sir.
All right. I don't care about you anymore. I don't care about you anymore. Let's take a look at this ladder diagram. I'm going to go through this, and if anybody has questions, I expect you to chime in and ask. Because if you don't ask questions, I'm assuming you know what I'm doing and everything makes sense. But this is pretty much lab 4. And we left off lab 3, and all you guys had was a start button and the motor starter coil. By the way, on your lab 3, you didn't have this. I put it in finally. This is what your prints should have looked like. You know, coming on your motor starter, the neutral coming off the coil, how it comes around to the side and goes through that normally closed contact. That's what your print should have looked like. Anyway, but some of you kind of noticed a little problem with the way that lab 3 ended up, because you pushed. What happened when you let go of the push button?
Motor
It
turned off.
stopped.
Yeah, when you depress the button, the motor would turn on because that coil would energize, closing those contacts and allowing current to go through the windings of the motor. But then when I let go of the button, it would stop. So pretty soon here, we're going to talk about something called seal-in contacts that are going to help take care of that. But for safety reasons, what we need to start doing is incorporating a stop push button. So remember I showed you the side of the push button the other day? And what is this set of contacts here, point B? Is that normally closed or normally open?
Those top two are normally closed.
Yeah, these are normally closed. These ones are normally open. So on the slider diagram, which is which?
The closed one would be your stop button.
Right. So this is normally closed. And this is normally open. I love my handwriting on this thing. I look like a freaking toddler. The action of any push button is always implied that the action is going to be in the downward direction. So if I push down on this button, what's going to happen?
It's going to close.
Yeah, it's going to make between these two contacts. Before I did that, there's no way that current can go through here, right? So if I do that, if I'm sitting there holding this button down, bloop, it's gonna energize the motor starter coil right here, and it's gonna spin the motor. But I need some way to stop that. Like, what if this gets stuck closed mechanically, just kind of sticks? I need to be able to stop it, right? Stop button allows me to open up that circuit. So I'm going to wire this up with your help, and we're going to test it out. This should do two things. It should start the motor, and it should turn this green light on. The stop button, if I push it, should open the circuit up and turn both of those off. So this would be lab number 4, close to it. And you guys remember that I'm recording these and putting them on YouTube, right?
Yeah.
So Don't feel like you can't ask me questions in the lab, but if you need to review this stuff before you come in the lab, or even whip your phone out in the lab and take a look at it, you're more than welcome to do that. Okay, so first things first, we need to number it. Right? So let's put a number here, 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 and here, and here. eBay, what's this number right here?
Professor?
What?
Which one?
This one right here.
That number. That L1. L1.
That is a 1.
1. Yeah.
Man, my freaking toddler handwriting on this thing sucks. Gavin, what's this one?
2.
That's a 3.
Oh, well, is this on a paper or something that you gave up Friday or something?
It would be on the recording of Friday's lecture.
Okay, that's why I didn't know that. Because I wasn't there Friday and I didn't know there was a recording or anything.
Yep. If I'm doing a lecture, I'm recording it and I'm putting it on. You remember how to find those recordings?
Yeah, I do. I just didn't know that you recorded the lab on Friday.
In this guy here, so.
Yep.
Bloop. All right, who's got this number? Right yonder.
3.
This number? These are all connected, so these must be a 4 as well, right?
Yeah.
Cool.
And the last 2 are 2.
Yes, sir. And do I need to label those on the wires?
Usually we use the white wire for it.
Right. So proud of you guys. All right, so I need to take off the control wiring that I did the other day. We can leave this, the black wires, right? In the control circuit or the power circuit. Because none of that's changing, right?
Yeah.
Okay, so while I'm, well, actually I don't really, I'll just take those off as I go. But wire number 1, I need to take it from where to where?
The load side of the transformer to the push button.
Yeah, and where on the transformer am I bringing it from?
The fuse.
Yeah, so this wire right here, it's technically a 1, but all that is coming off of X1 or X2, whichever one you used, and coming up to the fuse, right? So is that one done on my trainer?
Yeah.
Yep. So I can put a check mark there and a check mark there. Now, if you guys get into these and you're not putting numbers on and you're not putting check marks on your print, I don't care. You have to have numbers on to get credit for the lab. But if you're not doing the check mark thing, that's fine. If you think you can get your head wrapped around this stuff, but these prints are going to get more and more complicated. So if you get 75% of the way through there and you're asking me a question about where you went wrong or something, and you don't have any check marks on there, I'm like, I don't know, like I'd start over, pull all the wires off and start over, because you have no way of looking at that and knowing what you have done. So the check mark thing is a recommendation. If I'm wiring something up, I'm doing it because it's an easy way to keep track of what you've done and where you put wires and where things need to go as you're approaching. Okay, so then coming off of this fuse on the transformer, this wire here, where do I need to take it?
To your stop button.
Stop button. So on one of these stop buttons, there's 2 wires, which would be where'd my freaking button just go? On that stop button inside of that junction box, I got 2 wires coming off of these 2 points, right? And they're normally closed. I need to pick one of those wires. First, I need to figure out which ones they are in my trainer. And some of you might have already done that on yours, figured out which ones all of these are. I kind of have already because I put red ones here, but let's say I want to use this top button. How do I figure out which one it is?
You put your meter to check for continuity, and then it would be, it should not beep and then beep when it's closed.
Right, but is the stop push button normally closed or normally open?
It's normally open. So it should beep and, sorry, yeah, I had it backwards.
Yeah, it's normally closed. Stop button is continuous from point to point until I push it and then it opens up, right? If I need to figure out which one this is, I should get a tone on both of these. And then if I push it, it should open up. So that's not it. These 2 must be. So the far right 2 terminals are that stop push button. So that means my wire number 1 needs to go to one of those 2 points. Feel me? You follow me? Picking up what I'm throwing down?
Yes, sir.
Call me sir, it's like putting an elevator in an outhouse. It don't belong. If you wanted to call me like sensei or master, or like El Jefe, or anybody got any other good ones?
I like El Jefe. That's
El
pretty
Jefe?
sweet.
Let's go with that one. I like that. I like that. Makes me feel like a man.
There we go.
All right. So before I move on, what should I do? Maybe put some check marks on this thing right yonder. Hey, those are done. Let's do wire number 3. Where does that need to go from and to?
The stop to the start.
Yeah. Now, I'm not going to go through and put labels on each of these for the sake of time. But don't forget to do that on your labs. But I don't want you to go all the way through there and say, hey, I'm done. And everything looks gorgeous and it's perfectly wired up and everything works. But you don't have any labels on there. So then you have to go through the entire thing and put labels on it. You know what I'm saying? I just don't want that for you guys because I care about you. But you don't believe me?
I don't know, you kind of laughed there.
Oh. All right, wire number 3. So I basically need a little jumper to go from this stop over to my start, right? And I remember from last time that these two guys right here are my start push button. So I'm just going to make a little jumper wire here. Bloop. Bloop. Wire number 3 is done. Wire number 4. Where do I need to take it?
Is that the one you already have it going, the motor starters? You just run another one out of the light?
Yeah, so I've already got a wire going from the other side of my start down to my motor starter coil. Is that right?
I think so.
Yeah, it's this wire right here, right? What if that wire wasn't there and I decided to take a number 4 wire from the start button to the light? Is that okay?
Probably, as long as you don't take it from the light to the starter.
Yeah, all of it's okay. I could take a wire from there to there. I could take a wire from here to here. I can take a wire from here to here. I can take a wire from there to there. It doesn't matter. Every number 4 is going to be energized at the same time, right? They're all going to be on the same potential. So that being said, I already have a wire from my start push button down to my motor starter coil. So I can look at my print and go, bloop, bloop. Now what? Are my 4s done?
Oh, you gotta connect one to ground, right?
This
Keep the
green
jumper
light,
onto your light.
right? You're not saying ground, are you? I can't hear you.
No, I meant green, sorry.
Yeah, this green pilot light, okay? That fella is right here on my trainer. You guys have stack lights on your trainers as well, okay? And then how these are made up is there's a hot that comes from each one of these lights, and the neutral is shared by all of them. So basically, each one of these red wires corresponds to one of these lights, and they all share a neutral, which I've got made up right here already. So basically, I need to get a number 4 wire that comes up to my green light, which happens to be right here on this terminal strip. Okay, this wire right here is going into that stack light and makes up to this green light. So I need a number 4 wire right here. Where should I get it from? Basically, what I'm saying is I need to make this up as a number 4. Where should I get that wire from?
Get it from the terminal the push button is, since it's closer.
That's the right answer. Right here. Could I bring it from right here?
It looks like it'd be a little bit harder to have a second wire on there.
Yeah, that's a good answer too. But I guess what I'm trying to say is, if I had number 4 wires all over this thing, I could pull from one of those locations to right here. It doesn't matter where I get it from because they all get energized at the same time, right? What makes the most sense is I have a number 4 right here. And then I don't know, somebody else mentioned also, not only is this further away, so you're using more copper, more wire to get there, but this is kind of a smaller terminal right here. This lug is meant to handle more wires. And as a rule of thumb, I would always limit your number of wires to 2 under each location if you can. If you can avoid putting, 5 wires under one terminal, if you can pull from a different place. But the thing in this scenario that makes most sense is go a wire number 4 from here over to here, because this is where my closest number 4 is. Make sense? So here's my green light. And some of you guys need to do a little bit better job of keeping your trainers a little neater. So try to train your wires into these C channels as best you can, okay? And bring that up here. And in my print, I can go like this, because I just put a wire from there to there. So are my 4s done now?
Yeah.
Yes, they are. So number 2s. Let's start with the motor starter, number 2. Is that one done?
Yes.
Yes, it is. And just to clear that up, what that wire is right here, this little bitty number 2 wire is on your motor starter. It is coming off of this terminal on this. What is this thing called?
It's the coil.
That's the coil. Okay. That's what creates the electromagnetism that holds the contacts together. Okay. So I've got a wire number 4 going to this place. And I need a 2 coming from here and going over to the side to this normally closed contact right here. And that's actually what this little jumper, this is put on there by the factory. That's actually what it's there to do. But I'm going to take a white wire and go from here to here. And actually that's already done on my trainer. So that one's done. And then where does this 2 go? The other side of that normally closed contact.
You go straight back to the neutral.
Yep. That would be this wire. And on my trainer, my 2 from my transformer, and I think all of yours probably is set up this way too, goes to this terminal strip right here. And these are all labeled number 2s. And this tab up here, what's the word for joining all those together? We just learned it from the homework.
Bonding.
Those are bonded by this little strip. So I could land a 2 or a white wire anywhere on here, and it would be joined to this white wire going back to the transformer. Which means that this wire on the bottom of my normally closed overload contact needs to come up and land right here, and it's already done. So that means this is done and this is done. Now what about my light? Remember I told you that these all share a neutral, and it's coming down to that same set of bonded terminal strips. So that one's already done as well. Now I can look at this diagram and see that nothing else needs to be made up, so I'm done. Okay. And I'm plugged in, so all I need to do is turn the disconnect on. When I do that, if I hit the start button, what's going to happen? Two things.
The motor and your light will go up.
The motor's going to spin because, where'd my mouse go? What the? There it is. The motor's going to spin because this coil is going to energize and close these. Right? And this green light's going to also turn on. So here we go. That was it. Oh, came back down. Okay. Ready? Hey, look at that. Just look at it. My motor's spinning and the green light's turning on. Isn't that cool?
Yeah.
Now what do you want to do? You want to take a little break or you want to muscle through? I just want to go through sealing contacts before we're all done. 3, 2, 1, vote.
Muscle through.
Here we go. To solve the problem of that. Oh, one more thing I forgot to show you. There's the stop button. Let me do that in a second. What the? What the is this? To solve the problem of when I let go of that push button, that motor stops. What if I want to push that button, let go, and it still keeps going? We need to put something in there that's called a seal in contact. How those work is like this. Right now, in its de-energized state, if this was all hooked up and energized, I have 120 volts difference of potential on all of this right here. Right? And is any current flowing from left to right? Or from 1 to 2?
No.
No.
No, because this is open and this is open. Correct?
Yeah.
Seal in contact maintains that current flow. So what happens is when I press the start button, this closes Now current is flowing to here. And just like a relay, when I energize this coil, it changes the state of any auxiliary contacts that are also mounted to that coil, which means this closes. It also means that this is parallel, so current is now flowing through here, correct? Let me back up and show you that again. I've pressed the start push button. This is energized. Just like a control relay, when this is energized, any contacts, normally open contacts that are on there, are going to change state. This normally open contact down here is mounted right to the motor starter. So when this coil gets energized, this closes. And because all of this is parallel, it allows current to flow here too. Right?
Yep.
So now that I have current flowing in this path as well, it's also going through here because this is parallel. But now the important part is right now I have current flowing through here, and all I did was press that start button. Now if I let go of the start button and this opens back up, is current still flowing through that coil? Yes, it is. You see how that works? That's a holding contact or a seal-in contact. People call it different things. I typically call it a holding contact. But that's how a holding contact circuit works. I'm going to show you where that is on your motor starter, and then we're going to hook this up. Okay, so here's your motor starter. Do you remember when I showed you this off guy right here? And I told you when this energizes, it pulls the contacts together and does this. Boop. And you see that indicator telling you that the coil is energized and it's on. There's a little tab on the side here. And watch what happens when I push this up. This is the exact same thing that happens on your starter when you energize this coil. It goes, boop. Now they make these little auxiliary contacts that you can slap on here. They basically just click into place. And they have tabs that grab onto this spot. So if they're open, normally open, when the coil energizes, it pulls this up and pulls two sets of contacts together. I'm going to show you that right now. Oh man. There you are. Okay, so here's what it looks like. This is an auxiliary contact. You'll see this mounted to the side of your motor starter, like so. Okay, looks something like that. You see how it's a normally open contact? That is, on your print, this guy. It's called an auxiliary contact, and we're going to use this to maintain this current going through here once I push the start button. How it works is on the back side, this little notch fit into this spot here. Okay, it's mechanical. It mechanically moves this. And inside here, it's going to be hard to see without taking this apart, but you're welcome to look at one of these de-energized. Basically, when this gets clicked in there, I don't remember how that clicks in. this one might be broken, which is why I have it separate. Oh, that's why. There we go. So that just snaps on there. Okay, this is that sealing contact. Now, when that coil energizes, it goes bloop, and it closes the set of contacts inside of here. I'll show you with my meter. On. Tell me if you can hear this tone.
Yeah, I hear it.
You hear it? Okay. This is normally open. And then I'm going to simulate this coil being energized. Maybe. Okay, so this is off. When you energize the coil, and it pulls those contacts together, now it's closed. Okay, see how that works? So let's do it. I'm going to go through a number of these quickly for the sake of time, but if you have any questions on how they are, this is a 1, 3, 3, 3, 4, 4, 4, 4, 2, 2, and there should be a set of normally closed contacts in there, but those are already there from the last one we did. So here we go. Comparing this to the last one we've done, all we're doing is adding the set of contacts. Everything else is the same on here. So basically all I need to do is add this wire and this wire. So on this auxiliary contact, which on mine is right here, make sure my disconnect's off. I need a number 3 to go here on one side, and I need a 4 to go on the other side. So where's my closest number 3 wire? Anybody remember?
We up at the push button.
Right. Basically, my only number 3 is right here, and it goes from here to this little jumper. So the closest one is going to be right here. Now in my print, this is done. Now I need a number 4. Those are all done too, by the way. Where's my closest number 4?
Be on the starter itself.
Yep. This one right here is a number 4. So all I have to do is put a little jumper wire from there to right there. Oh yeah. So that wires in, which means this is done. Am I ready to go? All in favor?
Yes.
Yeah, we're done. We're ready. Now the only difference is when I push this button, the motor should still spin, the green light should come on, but when I let go of the button, that should all stay on. Woo! Pretty cool, right? Everybody understand the concept of the sealing and how that all works?
Yes, sir.
So how do I stop the motor? How do I turn it off?
Hit the stop button.
Hit the stop button. That interrupts current flow right here, opens the circuit up, and you basically start over. So now it stays on. Now it turns off. That's your basic stop-start station. Everybody cool with that?
Yes.
Questions on anything we covered today?
Yes. If we do end up with more than 2 wires on a terminal, that's something we use a wire net and make like a jumper onto it, or what would be?
No, on these we should never need any wire nuts. I mean, if you have a question about, hey, like, here's the thing, it comes down to kind of common sense, right? So these are really small. What I'm pointing to here is right here. These are pretty small, okay? If it's me and there is code here, then I'm not even really sure what it is, but it's kind of common sense that maybe one on one side here, one wire there, and one on here, right? I would definitely avoid putting more than 2 on these. These lugs, they're a lot bigger and they're designed to take more wires. So rule of thumb is try to limit it to 2 per connection point, but you could go above and beyond that if you had to. And if you ever have a question on what makes more sense or what you should do, just ask me. Anybody else? All right, then I'm going to cut you loose and we'll see you in class Wednesday morning. We'll do a little bit of lecture and your homework for chapter 2 should be due next Monday then, the 5th. Yep, chapter 2, 9 a.m. Okie doke.
When was that quiz going to be?
The quiz will probably be Wednesday the 7th because it's combined chapters 1 and 2. And if I remember right, all it is straight out of your homework. You'll have a random set of questions based on your homework, all multiple choice. If it's different than that, I'll let you know.
Okay.
We'll plan on taking the quiz on the 7th over chapters 1 and 2. 10-4?
10-4.
All right, y'all. You have a good rest of your Monday, and I'll see you Wednesday.
All right. Thank you.
See you, Zach.
I'll put the video up on YouTube as soon as it processes.
All right.
All right.
We're in person Wednesday.
Yep, in person. Come into class on Wednesday at 9.
Okay, sounds good.
All right.
Sounds good. Have a good one, Zach.
See you guys.
See ya.
Yeah.
See y'all. Have faith.
Yeah. So you said it in class Wednesday?
Yep. Come
Okay.
into class Wednesday morning.